So, welcome back to day one, and we are in part 3, section 3, talking about penalized regression. So we have seen before that ordinary least squares leads to overfitting at some point when we add nonlinear features, so direction terms and polynomials. Yeah, we have done that step by step and saw that at some point there's a problem with the fit in the test set. So penalized regression is one of those models that allows to avoid overfitting, but is fairly close to the actual regression setup or the OLS regression we are quite used to. So how does it do it? By including a penalty on model complexity using the mean square errors here from the test set. So using the information that we have in the data that we don't use for training, don't use for estimation. So specifically, penalized regression adds a penalty to coefficients, yeah? So to force them towards 0, limiting the effect of any specific feature here, xi. So this is then inherent to reduce the complexity by dropping variables. So how does it look? So we minimize not only the sum of squares, but also a penalty. Yeah? So we have added above sum of squares, you see here, this penalty, oops, go back, so this penalty lambda of beta. So the lambda here is a weight on the penalty and is called a tuning parameter. So the size of the lambda is now determined by using information from the test set. Well, choosing a linear model that we are used to in the context of econometrics or usual econometric analysis is actually some form of penalized regression. So choosing a linear model means linear in variables. So we don't include any features like squares or interaction terms or something like that. But what does it really mean? It means that we have a prior weight, a prior penalty on these variables, on any injection term or power of these features, and it's infinity. So we know they would never enter the model, so we can exclude them beforehand. We don't know this, but we assume that they're infinity and we can exclude them beforehand. So that means we actually do not let the data speak on what is important, but make this by assumption. That also avoids overfitting, but we might not have left in the features that matter for prediction. Nevertheless, this is a generally accepted method to avoid overfitting in econometrics. So in econometrics or in economics papers, one usually has to defend if one uses a higher nonlinear functional form, so with other features of higher order. But one does not have to defend quite often why a linear model is appropriate. So the lasso is one of the forms of penalized regressions, and a fairly famous one by now because it has shown success in a lot of different contexts. So the name lasso comes from least absolute shrinkage and selection operator. And this procedure can actually force some betas to be 0. So in some way, it performs a feature selection out of a larger group of features that are available here for prediction. But what it does, it actually introduces regularization bias. So that means the coefficients that we estimate, they are biased because we add a penalty and deviate from ordinary least squares, which is a method that would yield unbiased estimates of coefficients as long as the data generation process is of that form. So therefore, we have to be careful here. We do not want to interpret coefficient as true marginal effects. So they're not good estimates, well, they're never true marginal effects, but we don't want to interpret them as good estimates of true marginal effects. So how does lasso work? There are different ways of expressing the lasso, the lasso formula here, or the actual approach. It can also be expressed as a quadratic constraint programming approach, but here it is more in the nature and the idea of the penalized regression. So beta hat lasso is the argument that minimizes, choosing betas, this objective function. And the first part here is related to the sum of squares, sum of squared residuals, multiplied by a half. We see here, however, the distinction of the constant parameter, beta 0, and here are the slope parameters of the features, the beta j going from j equal 1 to p, being the overall number here of features. So now, this is the penalty. So the penalty in lasso is related to the absolute value of the coefficients. Yeah, and lambda is now the weight by which this penalty gets into the overall objective function. So higher lambda makes this more important relative to reducing the sum of squares. So be careful here. This only goes from j equal 1 to p, so the intercept is excluded. All right, so one of the things we see here on the right side is, well, no lambda, but the idea here is now what happens, how are features selected as we increase the penalty. Just have to be careful here because we have the direction here a little bit different. What we see down here is a shrinkage factor. And the shrinkage factor is not equal to lambda, as it says here. So I'm doing now something clear here. Ignore this here for a moment. Okay. So the shrinkage factor is related to the lambda, but it actually increases as lambda goes down. So as the penalty gets smaller, the shrinkage factor increases. So when we go from left to right, the penalty gets smaller. In the beginning, a shrinkage factor of 0, meaning a very high penalty, no coefficient really enters our model. All of them are 0. But when we decrease the penalty, then we have the first one entering, and it also increases in size as the penalty goes down. And as we further decrease the penalty going this direction, more and more coefficients get away from 0. More variables are selected into the model. And soon we're going to see something in this general idea here for our deforestation model. Well, lasso is just one of these penalized regression approaches, and there are 2 others that are used, ridge and elastic net, that are quite often used, that are also available in prepackaged routines in several software environments. So what do they differ by? Well, by the actual type of the penalty. So we have just seen here that lasso was here lambda times the sum of the absolute values of beta. For ridge, the penalty is lambda times the lambda times the sum of the beta squared. So we have a different objective function that in principle penalizes specific beta outliers in a stronger way. So the elastic net is actually just the combination of the two. It's a weighted sum of the two. So we have the lambda determining the size of the penalty overall. And then we have the sum of alpha plus beta squared plus 1 minus alpha times the absolute value of beta. So alpha is the weighting parameter between the two types of penalties related to beta. And this way we can combine both worlds. Now we get also an additional tuning parameter here for predicting the test set. So not only alpha, but we also get here, not only lambda, but we also get here the alphas, choosing between the two. So if you look at the geometry of now lasso compared to ridge regression, again, elastic net is just the weighted combination of both, then you see that the lasso is more, is not as smooth. Well, we typically have, what we see are contours, So combinations of beta 1 and beta 2 that have the same penalty. And if we move on this circle here, then we have the same penalty associated with those combinations of beta 2 and beta 1. Well, for the lasso, this contour has corners. It's not round. So it's a little bit different how combinations of beta 1 and beta 2 are weighted here in the overall penalty. Again, the squared penalty in the ridge regression is not so good for, or will more heavily penalize single betas being very large. Well, we can also look at these penalty function in a three-dimensional way. So we have here beta 1 in one dimension and beta 2 in the other dimension, and here we have the penalty in the vertical dimension. And again, we have this sort of smooth thing for the ridge regression, and we have the point at the corner, the one with edges here for the lasso. How do we choose the weight, this tuning parameter lambda, in the context of the machine learning application here of such penalized regressions? The problem is, if it's too large, then it can cause the model to lose information. So we have underfitting. If we push out too many of those variables, and ultimately have no variables in there, then we simply have a mean model, one that is unconditional with respect to the features. It can also be too small, then that's what we have seen. It can lead to overfitting. Well, what we use is cross-validation. So this is really sort of the nature, or part of the nature of the machine learning. We let the data speak and choose the optimal lambda. So we can choose a set or grid of candidate lambdas. And if you go to the notebook and continue with the lasso part of things that we have prepared, this is actually done there. You can see it and actually run cell after cell to produce what you will also see here on the coming slides. So we first choose a set of candidate lambdas, then we split the data into groups. So we do a cross-validation, train on n-1 sets and test on the last set. And we repeat it now, leaving another one of the groups as the test set. So for each lambda, we compute the average prediction error over all folds. So that means we go through all the steps where we leave out always a different test data set. And at the end, we collect and see what is the best lambda over all these folds. So when we do that here for our deforestation example, so we put lasso in action, we determine the optimal lambda for deforestation, then we get to this result. What we see here in the orange line is now the change in the mean square error as we increase the lambda, so as we increase the penalty. So we are successively forcing coefficients to get towards zero, and at some point also throwing them out. And we see that the mean square error is minimal here at that level of lambda. Well, we see also that for the train part, which is not really so relevant, we have increasing mean square error as we increase the penalty. That is not surprising because we know the more variables we have in there, so the further we are over here, the lower the mean square error or the higher the R square of our model. So we can also look at this now from the coefficient point of view. So here we vary the lambdas over a wider range to cross-validation to get the optimal lambda at some point. But we also see here as we decrease the penalty how the features enter the model that are relevant for our deforestation prediction. So we see this one here entering first at fairly high level of lambdas, and that is the variable cropland. Okay. Some enter a little later, but then reach quite high values as we further decrease the penalty. So this is related here to the population density. So this way we can see the relative, in some way also the relative importance of these features for prediction, because what determines them coming in to the model when we go here from left to right is how much they matter for the mean square error. All right, so far here for day 1. There are additional resources that you find here in these behind these links that allow you to go deeper, maybe to answer questions later, or if you have time now, already before the lab or the question and answer session that is coming up. So you can find information on bias versus variance in machine learning, on lasso and ridge regression and how you can deal with that in sklearn, so something we do in the notebook. Also on ridge and lasso specifically from the theory side, and also the elastic net. You get some nice statistical representation in this Stanford link here. So thanks for your attention, and I look forward to meet you soon in a live session here on day 1.